we've looked at, including this one, something which we can classify as India-scale societal problem, so social issues and things like that. So what we move on to now is we can classify as like aspirational or India pride, that kind of thing, which is landing on the moon as a private company. So you hear about SpaceX, which is a launcher. So we're talking about, and I'll invite Dr. P.S. Nair to talk about the details of it. The lunar lander and the rover completely built indigenously as a private company. Okay. A brief introduction about the speaker is that, PhD, as I said, from IISc in the 70s, when IISc was, the director of IISc was Professor Satish Dhawan, with whom he worked later and at ISRO. And he was the Satish Dhawan professor at ISRO for quite some time. He has led projects, 2 spacecraft missions. He's been the chairman of a number of review committees, and was involved in the space mission at ISRO since Aryabhat, right, until Chandrayaan-1. So a long-spanning career. And after retiring from ISRO, he joined Team Indus, which has this mission. And if you play Hearts, you know that in Hearts, it's moonshot, right? So literally, they have moonshot in their hearts. And he leads the structures and mechanisms group over there. They call him the Jedi Knight, Yoda, probably. So with that, I think I'll invite him to talk about the mission to land on the moon.
Okay, thank you, Dr. Pandey. Because of the limitations of the time, I would like to straight get into the subject. I am basically going to explain to you a very complex and technologically challenging problem done by a small private industry. Actually, it was a startup, but now it has become older, so I don't call it a startup. So the subject is development of robotic lunar exploration missions, which will mean that we have to develop a few systems. Basically, the Team Indus, popularly known as Team Indus, the actual name is Axiom Research Laboratories, is working on a robotic exploration missions. Not one mission, many missions it is working to go to moon. So this involves a lander spacecraft and a rover also. So this is first by any private industry, and if it after it lands, it will really make a milestone. You know, only Americans, Russians, and Chinese have so far managed to land on moon. Chinese was the last, which has gone on to the non-visible side of the moon. Now, there is a small background to how this Team Indus came into existence, so I would like to explain to you. You would have heard about a Google Lunar X Prize competition, which kicked up a lot of interest in all private industries all over the world. And Team Indus was the only team from India to be taking up the challenge. And of course, nobody was ready to go to moon when, as per the original schedule, so the competition itself was ended up. And Team Indus was on the top of the whole world teams when the competition ended actually. And the challenges are very many, the technological and others. In fact, others are much more challenging sometimes. I will try to explain to you how this team Indus met these technological challenges. I will not deal with the other challenges. Before the competition ended, as well as later on now and in future.
We leave as we came, and God willing, as we shall return.
Today, we're challenging private teams from around the world to design and build robotic explorers and race them to the surface of the moon.
To be the first privately funded enterprise to build and land a rover on the moon.
$30 million of money to reinvent how we get to space, how we get to the moon.
These people are trying to demystify this entire concept of a lunar exploration. I think this is exceptional.
I don't care who you are, what you've done before. The first person to make that happen wins.
We're doing the aerospace solution, which hopefully is going to land on the moon soon.
I think we ran out of doing crazy stuff on planet Earth, so that's the next phase to go.
Everyone here realizes it, that you're making history here, and I think that's what drives people the most.
The prize money on offer is far less than what it is going to cost any team to do this, and that's the challenge.
We have the talent, we have the caliber, we have the initiative, and we have the motivation. Let's compete at the world and see if we can win.
And I think when they win, India wins.
Yeah, so that was the background in which the team Indus came into being. And of course, this shows the moon and where we are going to land in the Mare Imbrium area for the first mission. And this project involves design and development of high performance lunar lander, which will go from Earth orbit to moon orbit. Then it will descend on the moon surface and soft land on a pre-planned, precisely on a pre-planned location. And the exploration of the lunar terrain itself is done by a all-terrain semi-autonomous rover, which can also carry payloads. It can do many things, including photography, sensing, and so on. So now the first step is to go from Earth to moon, and there is a design of an optimized spacecraft trajectory from Earth orbit to the moon orbit, and then of course a fully autonomous descent terminating on the in hover and precise landing, and using a qualified set of rockets, small rockets, thrusters. And this is one major task. And of course, this has to incorporate all the variabilities in the gravity field, moon as well as Earth. It is not a simple first term approximation because of the changes in geometry, changes in the properties of the Earth locally. There are a lot of higher order terms and complex influences to be incorporated to be precise. So this is the outline of the trajectory. And the last descending lunar descent is really very critical. This 900 seconds is the most critical phase. It is totally autonomous. We have no way of intervening. And it involves onboard real-time processing of a lot of data, cameras, sensors, distance measuring equipment, and so on, and onboard health data. And the guidance algorithms will have to incorporate all these possible performance deviations, inaccuracies, and failure modes, And the biggest problem is this cannot be fully simulated on the ground before you actually do the work. So this is one of the most difficult things, and of course you will exercise the computer processing capacity and simplified algorithms and fault tolerant ways of doing things. So this is how it lands. Now, in addition to going there, doing the rover experiment, there are a lot of payloads and collaborators. I just wanted to mention that we have some cameras flying from Cannes, France. Similarly, there are a rover from Japan who wanted to fly with us. Then there is some biological experiments from astrobiology to see what happens on the moon with biological processes. And similarly, there are shields later on when human beings want to live, how to protect from radiation, and similar several experiments are there. So this is to be able to collaborate, because while you build the lander, you have to take on whoever is interested and whatever experiments are of interest to people. Now, the first and biggest task is building a lander spacecraft. So the most important thing is converting the mission objectives into a practically realizable lander design, very high in performance, high in reliability, and also adaptability, because things will change with time, because the next mission may be different, so we have to make it adaptable also. These are all big challenges and can only be met by application of, I wanted to say, because I have been hearing artificial intelligence, a lot of natural human intelligence and creativity, because without this you cannot attempt a design of a complex configuration of the lander spacecraft. And it also requires experience and expertise in all these advanced technologies. And Team Indus is now in the final lap of realizing such a lander rover system after the GLXP closure. So this is in fact an actual picture of the lander for the first mission. And the lander design involves actually is a synthesis of almost all branches of engineering for optimizing the mission performance and reliability, with the constraints on, of course, time, technology, and resource. So we, for example, are using a combination of all advanced materials, whether it is thin, tow, carbon fiber composites, different structural forms like honeycomb sandwich construction, different various other elements like energy absorbing elements when it lands, and there are several other new technologies, several first being part of this system. And the design, validation and qualification is achieved by a combination of elaborate numerical modeling and simulation, because almost everything except that final landing is simulated numerically, digitally, and then whatever tolerances, fault possibilities using Monte Carlo and several other techniques is studied. And this involves extensive and intelligent use of computer-aided inspection, testing, modeling, and simulation tools. And of course, the onboard system, there are several systems. I just listed avionics, guidance and navigation control, electrical power systems. All these are integrated with computer hardware and software, and these only can make the mission possible. And we have a unified propulsion system, which is a combination of small thrusters and big thruster. And another first, world first, which is done is to be able to get variable thrust. We are using a digital control, that means pulsing the big engine with the different durations to get effectively the variable thrust. This is also a first in this kind of missions. And this is the, I said about the descent. Can you just animate it? This is just to simulate as the lander comes to the moon, how it will look, the land or the terrain will look. And this is being constantly monitored by the cameras, and this is also being processed and used in case there is a big hurdle or a crater, then you have to move away and then land in a safer place. So this kind of is totally autonomous. Of course, this is a simulated picture using the some of the data available in the literature. And this is another near the landing. Can you run this? So it is basically this is that square is the area where it is going to land. So it is just amplifying and showing as it comes closer, and it will land in a selected safe space. Again, this is a simulation, but actually the spacecraft will be doing this in real time. I think it will finally spot very accurately within few meters. It will land in a very safe, without big mounds or craters or stones, in a safe location. So we will go to the next. Now the next after landing is the surface operations, and this is done, as I mentioned, using a Lunar rover. Of course, after it is landing, after the dust is settled, after all the health of the systems are all checked, the rover is simply released and dropped half a meter. Of course, moon has low gravity, 1/6 of Earth, so it is quite safe to drop half a meter. This is a micro rover. It is around 6 kilograms or 7 kilograms. It's an all-terrain, 4-wheel driven vehicle. You can see a picture of the rover. It is semi-autonomous. It's all-terrain, and you have a very optimized design, multiple materials to reduce the mass and so on. We have a solar-powered. It is totally solar-powered. And high definition cameras with pan and tilt and so on. And this is just to show you how the tests are done. This balloon is tied on the top of the rover essentially to reduce the weight to 1/6, and then you are doing the steering and all that. In fact, all this will move. I think because of lack of time, I think we will move forward. Yeah, this is some of the tests done. Essentially, how it turns. Without steering, you can turn by coordinating the velocity, rotation of the wheels, actually. You can even make a perfect 180-degree turn. And similarly, slope mounting also is tested. These are all tests on the ground done. This is a photo camera picture from the rover of the terrain, just to show as an example. This is actually on the ground in our test laboratory. Yeah, now I just wanted to mention what is in store for future. So the lander and rover is in the final phase, ready, and it will be fine-tuned with the payloads, because there is no more GLXP competition. GLXP competition was essentially landing on the moon, sending the rover for 500 meters, then you are won. Actually, you don't need to do anything. But now you have to fly payloads, and there are several other mission requirements. So the lander and the rover which I showed is for that modified mission. Now we are planning, this is the first one is what the first mission Z01 which I explained so far, which will go next year, supposed to go next year. And we have a series of other landers and rovers in the pipeline, which is being developed. And this lunar exploration and lander and rover can have differing degrees of freedom depending on where you land on the moon, for example. If it is on the polar side, see, normally near equator, the 1 day in moon is 14 Earth days of day and 14 Earth days of night. So, and whereas it is in the pole, 1 day maybe 150 Earth days, and the remaining will be night of the year. So, depending on that, the illumination conditions, solar illumination conditions, the communication with Earth, all that will change. So, for example, for almost 22 days, you may have no RF link with the rover or the lander, in which case you need to be totally autonomous during that period, at least. Of course, you can be autonomous longer. So, here the role of the totally autonomous rovers and lander comes into play, and with several weeks, because thermal is a big problem. Moon is around 120 degrees Celsius near noon. You cannot even touch. So, on that only we have landed and is sitting. So, you have to do a lot of work in thermal control, for example. And so, this requires, as I see, a lot of technologies from artificial intelligence and data processing and decision making. Of course, this will call for the highest level of such technologies, because you have to learn after doing that exploration. And development of these landers and rovers for the next missions and follow-up is what Team Indus will be doing after this first mission. So, thank you. I think next, I wanted to show the team. This is the Team Indus. When it started, just a photo of the team, and then thank you.
Thank you. We'll take a couple of questions.
So, I'm just wondering, where do you actually do the field testing for these? Do you create test beds?
Yeah, actually, one challenge is to create the lunar terrain. So, it is actually created in our own workplace. Getting the sand is another problem, because the moon sand is very, very fine, it seems. They were even comparing with talcum powder. So, it is, so we could gather the finest possible sand. I think it was gathered from somewhere in Coimbatore and all that. But it is still not as good as moon soil. So, this is created in the campus with all the likely terrains, stones, and all that simulated. So, it is done in-house, I would say. And then the rover.
How big would that test?
No, it need not be very big. It can be, say, even 100 by 100 feet. You can create different things and do, because the continuous sort of sustained driving is not the real issue, actually. But you can run, because thermal is a problem. If you continuously run, if the temperature is hot, then you have to take rest for some time, because motor gets heated up because of the high power. So, these kind of things are there. So, the test bed for this is in-house. Of course, there are US laboratories opening, available better sand and so on and all that. So, because teaching the cost and time is also an important thing. So, it is done in Bangalore, actually.
Thank you.
The question I was going to ask, well, I am going to ask is, of course, this is a commercial venture. So, I assume you have funding, seek funding, as well as, well, a commercial offering, right, for others.
Correct.
I mean, they may not be individuals, but can you say that?
Yeah, so actually the biggest challenge is that I said technological and others. So, because having a will to do moon project is certainly possible, and the Team Indus has shown it. ISRO has done it, but Team Indus, of course, without ISRO, Team Indus would not have been there. This muscle power is got, the knowledge power is got from ISRO. There is no doubt about it. I am myself an example. So the real issue is that there has to be money, the commercial interest of payloads, for example. Right now, the Team Indus is envisaging NASA's wanting to fly payloads on payment. So NASA will say this payloads has to be flown to moon to do certain experiments, so they will pay for it. So like this, there are a few payloads from the Indian Institute of Astrophysics. Like that, there are several enterprises are interested in doing experiments on the moon. So instead of they are developing everything, we fly, and for example, the Japanese rover, they pay. They were also part of the competition, only for the rover competition. So they pay for flying to moon. So like that, you have to make it viable. So, but it is very costly. The launch vehicle, launch itself is as costly as the cost of the lander. So that is how it becomes. So it is a big challenge, in fact, and it has to be the interest from the various scientists and technologists to do experiments and science on moon or on the way. Also you can do.
Thank you very much. Thanks.
Yeah. Sir, Dr. Pandey, I have a question. Yes. Sir, I just want to know that how old is Team Indus, first of all? That is the first question. And how much time it has taken to build this kind of close to perfect simulation environment?
See, nothing is perfect, let me tell you that.
Close to perfect, right?
Yeah. No, because the mathematical models, numerical simulation has improved so much that we can greatly rely on this now compared to, say, 10 years back. When Apollo was built, that I would say is archaic technology, the Apollo technology. Now, your first question is when Team Indus started. Actually, I am telling you, the competition, when competition started, the last day only it started actually. It was 2012, I think. Around that time, the Google, a few people pooled their pocket money and other deposits and all that and applied for this competition. Rahul was the chief actually. So that is how it started. But it came to Bangalore. I got involved after it came to Bangalore. It was in 2013. 2013, it came to Bangalore. After that, only the real technological build-up started. And so it is now almost 5 years time since it started seriously. It never was more than 100 people. I'm just telling you. And that all youngsters, fresh engineers from college, except a few of us from ISRO, all were almost fresh engineers, no knowledge in engineering, I would say. Computer scientists I don't call engineers. I'm saying hard engineering. So they had no knowledge of mechanical engineering or structural engineering or thermodynamics or fluid dynamics or anything like that. So propulsion or so.
As Dr. Pandey also told, this must be very, very funding intensive exercise, this whole thing. So is Government of India upbeat about this initiative?
No, Government of India contribution is zero. I mean, there are many people like Nilekani, many other people, including Wipro and several other people have contributed, wanting to push India to succeed into this competition. Of course, now slightly different, but now they are trying to make it commercial. People to finance, because once US is interested, NASA is interested, European agencies are interested. So you have to compete globally, then only you can succeed in India. Once you succeed elsewhere, you will succeed in India also. So this is the moral of the story.
Thanks. Thank you for taking us on a journey where no one, or rather not too many, have gone before.
I have a question, sir.
Yeah. Oh, okay. Where? Sorry. Okay, Jai.
Just out of curiosity, what kind of processors are used in the control part of your
I don't remember the
I mean, are they like commodity processors, or are these like special?
Yeah, see, the only main thing is the radiation hardened space grade processors are used for the crucial avionics and all that. They are trying to do the industrial grade components and processors. But only thing is reliability is a big issue because the radiation, particularly single event upsets, and the processors are prone to, and once processor doesn't work, nothing works. So that kind of a problem is there. So in fact, the capability of the processor is not comparable with some of the best processors available on the ground, but the reliability is the main issue.
And do you use like OS like VxWorks, like real-time operating systems? Or
real-time operating system is anyway required. Okay. So I'm not really a computer specialist.
Okay.
Yeah. Okay. But you can get it from the even website. They have given the details of the what we call the integrated avionics, even electrical power systems, GNC, everything is integrated into one package, where everything is there. Thank you.